In this video, we will discuss rules of exponents. So first of all, vocabulary. What is a monomial? Monomial is a number, a variable, or product of a number and one or more variables. For example, 34xy. It's a product of numbers and more than one variable. Another example can be 7a squared b. It's a product of a number, a variable, or one or more variables. Okay, so 7x is also a monomial. 3 is also a monomial because you can just think of 3 times x to the 0 power, or 3x to the third, y to the second, z to the fifth is also a monomial because it's a product of number and one or more variables. When we have a term written with the as a power, so we have the number raised to the exponent. The bottom number is called the base. The one which is raised to the power is called the exponent. 5 squared does not mean 5 times 2. It means 5 multiplied with itself 2 times, which is 25. Negative 5 to the second power is negative 5 times negative 5, which is positive 25. Negative 5 to the second power without any parentheses means like negative 1 times 5 to the second power, which is negative 1 times 5 times 5, which is negative 25. Okay, so we're going to discuss some rules of exponents. Memorize them, remember them. They are used a lot in algebra when we are dealing with polynomials. The first rule is a to the power m times a to the power n is equal to a to the power m plus n. That means if you're multiplying two numbers with the same basis, then add the exponents. Multiplying two numbers with the same basis, add the exponents. And this works with more than two numbers as well. So here's our first example. Multiplying two numbers with the same basis, exponents are different, so this is going to equal 5 to the power 2 plus 6, which is 5 to the 8th power. And really, if you write 5 to the second power, you expand it, it's 5 times 5, and 5 to the 6th power is 5 times 5 times 5 times 5 times 5. So altogether you have 8 fives, which is same thing as 5 to the 8th power. So remember, when the bases are same and you're multiplying, add the exponents. Okay, only when the bases are same. If you had like 3 to the second power times 5 to the 6th power, you really cannot use this rule because your bases are different. Right? Another example, y to the 4th times y to the 3rd times y. This actually means y to the first power. When you don't see an exponent, there is a hidden one as an exponent over there. So this is going to equal y to the 4 plus 3 plus 1, which is 4 plus 3, 7 plus 1 is 8. So y to the 8th power, which means we have total 8 y's, which we can see. This is 4 y's, 3 y's, and another y, total 8 y's. Next, we can see now we are making it more fun. There's numbers, variables, and exponents. So first thing, when you're multiplying, you want to take care of the signs. Sign means positives and negatives, and then you want to multiply the coefficients, and then you want to take care of the variables. Okay, so both are positive, so I'm gonna have a positive answer. Multiply the coefficients. 7 times 6 is 42, and then we have y to the 5th times y. Well, there is a hidden one we just talked about, and we will be adding the exponents because bases are same. Okay, so 42y to the 6th power is what we're left with. Next, we are going to take care of the signs first. So negative times a positive number is going to be negative. 3 times 5 is 15. X to the second times x to the first power, we're going to add the exponents. X to the third. Y to the 7 times y to the 6th is y to the 13. That's the end product here. Next, we have quotient of powers. When we have the same basis and we are dividing, we subtract the exponents. Okay, if we are dividing two numbers with the same base, subtract the exponents. All right, let's see. Y to the 6th over y. This means there's a hidden one over here. We're going to subtract the exponents, which means y to the 5th. If you really want to see it in the expanded form, y to the 6th means y times y times y times y times y. I guess I got 6 y's now, yeah? and then there's 1y in the denominator. Really, when we are dividing, if we have same thing on the top and bottom, numerator and denominator, we can get rid of it. So we're just left with 5y's, which is y to the 5th power. Okay, this really saves you a lot of time by not expanding all the, you don't have to expand all these terms, and you can um, go ahead and simplify without expanding by using the rules of exponents. Okay, 6 to the power 13 divided by 6 squared. Same basis, subtract the exponents. That turns out to be 13 take away 2 is 11. 13 take away 2 is 11, okay? So 6 to the 11th power. Again, you could expand and say, okay, there's 13 sixes and there's 2 sixes here. When you cancel them, you still have 11 sixes back, which is 6 to the 11th power. Now we're making it more fun. We have numbers, coefficients included as well. So we're going to first take care of the numbers, then the variables. Okay, 10 divided by 15. Is it possible to simplify this fraction? Of course, we can divide top and bottom with a 5, which gives me 2/3. Now, a to the power 7 on the top, a to the 5th power in the, a to the power 7 in the numerator, a to the 5th power in denominator. Which means we can subtract the exponent. So 7 take away 5, and then b to the power 9 take away 9. All right. Actually, before, we haven't talked about the 0 exponent yet. So let's just say, since we have same thing in the numerator and same thing in the denominator, we can get rid of it. So no more b's left. B's are gone. A to the power 7 minus 5 is 2. So 2/3 a squared is what we're left with. Let's see the next rule, 0 exponent. The 0 exponent, anything raised to the 0 power is 1. Okay, anything raised to the 0 power is 1. All right, so let's explore 8 to the 2nd over 8 to the 2nd. What does it really mean? Let's just go ahead and expand it. 8 to the 2nd power means 8 times 8. Again, 8 to the 2nd means 8 times 8. So when we cancel and cancel, we're dividing same thing with itself. This is going to equal 1. If you want to open up, operate on the, perform the exponential operation, 8 to the 2nd power is 64 divided by 64, which is also going to equal 1. So you can think of it either way. So anything raised to the 0 power, which if you use the rule of subtracting exponents, we just did talk about that if you are dividing and your bases are same, then you can go ahead and simply subtract the exponents, which turns out to be a to the 0. So that tells me that anything to the 0 power is equal to 1. 0 to the 0 power is not equal to 1, okay? Keep in mind, other than 0, any other number raised to the 0 power is equal to 1. So here's one example. Do I need to care or bother about what's in the parentheses? Not really, because anything to the 0 power is 1. We don't want the inside to be equal to 0, because 0 to the 0 power is not equal to 1. That's indeterminate. You will learn more about it when you get to calculus. Okay, it's very important, indeterminate form. Here's the next example. X to the 0 power, 8 is not raised to the 0 power. Keep in mind, 8 is not raised to the 0 power. It's like 8 times x to the 0 power plus 5. What is x to the 0 power? X to the 0 power is 1, which turns out to be 8 plus 5. And 8 plus 5 is 13. And that's our answer. If you had 8x to the 0 plus 5, that was a different story. That was a different problem. Because now whole thing, 8 and x are both raised to the 0 power. Anything to the 0 power is 1. So that answer would have been 6. Next, we're going to talk about the rules of negative exponents. Rule of negative exponent is anytime you have a negative exponent in the numerator, you can bring it to the bottom and make it positive. If you have a negative exponent in the denominator, you can take it to the numerator and make it positive. For any non-zero number, a raised to a negative exponent, place the power in denominator to rewrite the power with the positive exponent. So you can bring it to the bottom and make it positive, okay? Now, why does that really work? So think about 2 to the 3rd power, 2 to the 2nd power, 2 to the 1st power, 2 to the 0 power, 2 to the -1 power, 2 to the -2 power. What is 2 to the third power, well, it's 8. 2 to the second power is 4. 2 to the first power is 2. 2 to the 0 power is 1. See, every time you're reducing the exponent by 1, you are dividing your right-handed term with the 2. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1 half. 1 half divided by 2 is 1 fourth. So you are dividing with the 2 as you're reducing the exponent, okay? And that continues to negative exponents as well. So let's explore b to the second power over b to the fifth power. This is going to equal b to the power 2 minus 5, which is b to the negative third power, and 1 over b to the third. That's what the rule says, that bring it to the denominator, make the exponent positive. Now, why is it true? Let's go ahead and expand these. B squared means b times b. B to the fifth means we have 5 b's in there. So 2 of the b's are gone, and that just leaves me with 1 over b to the third power. 2 to the negative 3 power, okay, bring it to the denominator, make the exponent positive, and I know 2 to the third power is 8. Negative 3 to the negative third power, well, 1 over negative 3 to the third power, which is 1 over negative 3 times negative 3 times negative 3. And that's 1 over negative 27. We usually write the negative as a coefficient, and then 1 over 27 as a fraction. Next rule of exponents is a number raised to an exponent, and there's another exponent outside, then these two exponents are going to multiply with each other. A to the power m to the power n, the m and n will multiply each other. If we raise a exponent to a power, then we multiply the exponents. Here's some examples. X to the second power to the 8th power, this is going to be x squared to the 8th power. That means 8 and 2 will multiply, which is x to the 16th power. Why? Let's go ahead and see. If we were to expand it, x squared, how many times do we have x squared? We have it 8 times. X squared times x squared times x squared times x squared. 1, 2, 3, 4, 5, 6, 7, 8. If we add all these exponents, that is equal to x to the 16th power. Next one looks more fun with the negative exponents, but hey, we can take care of the negative exponents later. Let's just go ahead and multiply the exponents. What's negative 3 times negative 4? It is positive 12. So this is going to equal y to the 12th power. Now, if we were to expand or simplify, use the rule of negative exponents, then this is what I have. Negative exponent means I can bring it to the bottom and make it positive. So we can do one at a time here, and then do the operation one more time. Now we'll be back in the numerator, right? I think it's faster and easier to just go ahead and multiply the exponents and see it's going to equal y to the 12th power. Next, power of a product. When you have a product and then a power outside, a product is raised to a power, the outer exponent goes to everything inside. Every single base inside gets raised to the outer exponent. Okay, this is confusing to students, especially when there's a coefficient involved. So let's check out the first problem. 4x to the third, y, z, everything raised to the third power. So we have a product of several terms inside, and there's an exponent outside. We need to keep in mind every single term inside will get the outer exponent. Okay, so it will be 4 to the third power, x to the third power, y to the third power, z to the third power. And we can use a rule over here that we just talked about, that if you raise an exponent to another exponent, they multiply. And 4 to the third power is 64. 4 times 4 times 4, 64, x to the 9th, y to the third, z to the third. Okay, next example, we have a negative exponent here. Negative exponent means we bring it to, we can do it two ways, but I'm gonna do this. I'm gonna bring everything to the denominator and make the outer exponent positive. And now every single base inside is going to get the outer exponent. So it turns out to be 1 over 49 x to the second power y to the negative 4 power. Again, the negative exponent in the denominator, I can take it to the numerator and make it positive. So y to the fourth power divided by 49x squared is what this turns out to be in the simplified form with no more negative exponents or no negative exponents. All right, next problem. Here again, I have a negative exponent outside and a negative exponent, several negative exponents inside. We can do them in any order. So I'm going to go ahead and first actually multiply every single exponent inside with the outer exponent, okay? Not the coefficients inside, but the exponents inside get multiplied with the outer exponent. So I will get 1 times negative 2 is negative 2. Negative 6 times negative 2 is 12. Negative 7 times negative 2 is 14. And 0 times negative 2 is 0. All right, simplification required now. Well, these two terms are fine. They have positive exponents and there's no more simplification that can be done on them. But 6 to the negative 2 power can be written as 6 to the second power in the denominator, positive exponent now. If you bring a negative exponent from numerator to denominator, it turns into positive. And z to the 0 power, it is equal to 1. So we don't need to write that because when you multiply something with 1, it still stays the same. If we want, we can write it as x to the 12, y to the 14 over 36, and that would be it. Next, we get power of a quotient, a over b to the power m. So if we are dividing if we have a quotient and it's raised to an exponent, every single base inside your quotient, both numerator and denominator, get that exponent. Or you can think of that the inner exponents will multiply with the outer exponent even if you have a quotient inside. It's very similar to the last rule, except we talked about the product inside. Now we're talking about a quotient inside. Okay, for any number a and b not equal to 0, we don't ever want our denominator to equal 0. That's a big domain restriction. So denominator cannot equal 0. We cannot divide by 0. We've talked about it's a big trouble. If the quotient of a and b is raised to a power, raise both the numerator and denominator to the given power. Okay, so inner exponents multiply with the outer exponents. Now here we are, 3/5 raised to the second power will be 3 to the second power over 5 to the second power, which turns out to be 9 over 25. And that's it. Cannot simplify it anymore. Again, keep in mind, every single exponent inside will multiply with the outer exponent. Okay, 2, every single exponent inside will multiply with the outer exponent. 2 to the second power is 4, a to the 10th power, b to the 14th power. Here's example number 3. Some negative exponents over here. Let's take care of the negative exponents first. Because a to the power negative 4 is in the numerator, I'm going to bring it in the denominator and make the exponent positive. Now I'm going to be taking care of the outer exponent. So every single exponent inside will multiply with the outer exponent. So 3 to the first power would become 3 to the third power divided by a to the power 4 times 3 is 12. B to the power 7 times 3 is 21. 3 to the third power is 27 divided by a to the 12th, b to the 21. No more simplification can be done over here, and that's our end product. Here's our last problem. Looks like a complicated problem. There's several terms with the negative exponents here. So let's go ahead and we can do it in multiple different ways. Because every single exponent inside is negative, I'm going to go ahead and multiply every single exponent inside with the outer exponent. So negative 2 times negative 6 is positive 12. Negative 5 times negative 6 is positive 30. And negative 11 times negative 6 is 66. A to the power 12th, b to the 30th power, and c to the 66th power. That's it. No more like bases. And that's the end of our video on exponents. So remember these rules of exponents that we've talked about, memorize them. Like I said earlier, they're very useful in algebra, especially when you're dealing with polynomials.